Hello and welcome. Let us discuss another solution for an in-class problem. For this particular problem, we are asked to compute P of A, where A corresponds to the event that when I roll 5 independent dice at the same time, I get 5 of a kind. What does that mean? Let us break this event together. So we know that we have 5 dice, right? Let's start by denoting each of those dice. X1, that's going to be the result of the very first dice. X2, it's going to be the result of the second dice, and so forth. Now, let us think together of what are the possible cases in which I could get 5 of a kind. So getting 5 of a kind implies that when I throw all my 5 dice, I get the exact same number. So that could happen if I throw all of them and I get all numbers once, but it could also happen if I get all number 2s or all number 3s and so forth until the number 6. So all 4s or 5s, all 6. Like this. So all of these scenarios, each particular row that I have drawn here corresponds to a specific possible scenario where I would still be getting all 5 of a kind. Now, let us start by practicing our notation. We can see here that all of these events are all linked here, ideally by my description, by a little and. So it has to be the case that I get the first one and 1, the second one a 1, the third one a 1, the fourth one a 1, the fifth one a 1, all those together at the same time. So this could all be linked with AND operators. So I could visualize this as having a little AND here, a little AND here, a little AND here, and a little AND here, and so forth for the remaining of the rows here. So you could already see that this slide looks very messy right now, but the only thing that I want to emphasize is that for all those possible cases in which I still get 5 of a kind, I could use this notation here to denote that all of these results per individual die had to be true at the same time. That's what we have here. The first die is a 1, and the second one is 1, and the third one is also 1, and the fourth one is a 1, and the fifth one is a 1 as well. That would be one case in which we get 5 of kind. Similarly, I could also have the second case where I have the first one is a 2, and the second one is a 2, and the third one is a 2, and the fourth one is a 2, and the fifth one is a 2. Again, I get another case where I get 5 of a kind, and so forth for the next. You can see here the little and symbols. Anyway, this is a good time for practice or group operators. So we can see here that this and becomes a little redundant. So we can start using here or group operator for and. We're going to remove all the individual elements here, and I'm going to have here a big and symbol that it's going to apply across all the possible dice that I have shown, such that all of them have to result in a 1. And because this is a group operator and it's kind of like iterating over all the dice that I have here, I would use here a little index I to indicate that this is the dice that is rotating. So it has to refer to the first die, the second die, the third die, the fourth die, and so forth. All of them have to be 1. I'm going to have here on the lower part here the initial value. So it starts at I equals 1, and it goes up until the upper boundary of 5. So again, what this is indicating is exactly what we had on notation below. The first dice is a 1, and the second dice, because it moves to the next integer, is also 1, and the third dice, we move to the next integer, is also 1, and so forth, until we get to the and. The last dice, which is going to be the number 5, the number 5 dice, or the dice number 5, the fifth dice that we have thrown, is also 1. And we can do that for all the remaining rows here. And you have seen here that I have had to rearrange the column so that it fits, but it's pretty much the same. So for all the possible values that I could get on a dice, in order for me to be able to say that I got 5 of a kind, it would have to be the same that all of the possible dice from the first die that I drop until the fifth one that I throw, until the fifth one that I throw, all of them fall on either a 1, a 2, a 3, a 4, a 5, or a 6. So now, at this particular moment in time, we are able to compute the probability that either of these individual scenarios happen. But that is not what we were asked to do. We're asked to do the total probability of getting 5 of a kind. And to do that, we're going to take advantage of the fact that, as we can see, all of these scenarios, yes, they are all the possible instances in which we could get 5 of a kind, but they are also mutually exclusive. It is impossible to get all 1s, but at the same time all 2s, and at the same time all 3s. It's not possible. Only one can be true at the same time. And that means that the way that we're going to compute the probability of getting 5 of a kind is by just summing these individual probabilities. How do we indicate that? Well, we can also use an OR indicator. We're going to use an OR indicator for groups, and we're going to be grouping all of these individual possible cases all together. The first thing to notice here is that I'm still going to preserve on the inside a very similar notation to what I had before. So I'm going to be using the AND across all the 5 dice that I'm going to be throwing, right? So I want them all to be a similar number. But now notice here that I have not specified it. Because this is the same operator, it just keeps iterating. I am now going to be able to place here outside the big OR operator and now have here an index that it's going to be updating, or that it's going to be moving across the 6 possible values that I can observe in a dice throw. So now I'm going to have here that the minimum value that I can place here is a 1, and the maximum would be a 6. And now here, with this notation here, what we have denoted is that the cases in which we get 5 of a kind, all of the 5 die that I'm throwing, here denoted with this little I, are going to result on the same value j, and that value j is going to consider all possible values from 1 to 6. And now we can turn this into an operation, and we know that because all these events are mutually exclusive, we can turn this OR directly into a big sum side. So we're going to be summing across all of these events. And we also know that all the dice being thrown are independent. So they are thrown simultaneously at the same time. What I get on a single die does not affect or should not affect what I get on the other dice. So this particular group AND could also be replaced by the product operator here. Notice here that we are now asked to replace here with the probability that any given die results on any given number. And we are told that this is a fair dice throw. So we know that there are 6 possible outcomes. And the probability of getting any given value, it doesn't even matter for me to specify. The probability that I get any possible number between 1 and 6 is always going to be 1/6. So now I have to multiply 1/6 5 times, right? That's what this product sign means. So this is equivalent of just placing here 1/6 to the 5th. All right, so let me rewrite that to make it look prettier. So we can now continue with the summation that we have here. We know that what this means is that we will be summing 1/6 times 1/6 to the 5th plus 1/6 to the 5th plus so forth, so forth 6 times. So we can simplify this as simply 6 times 1/6 to the 5th. And then we know that we can simplify this by moving this exponent to the numerator and the denominator. And if we simplify, we know that this is going to stay a 1. And the number below, it's going to be now, I'm using my calculator, of course. Here, this is, 7,776. We multiply our 6 here. So this moves to our numerator. And luckily, we find that if we divide this whole thing by 6, we can simplify again. So we divide now the denominator by 6. And we get 1,296. And that is the correct answer for this exercise. So a little long, but hopefully not too tricky. All right, see you guys.